Now, selection sort is yet another n squared sorting algorithm. And the way to think about this with respect to our card analogy is that you have your hand of cards in front of you, and you want to find the card that goes at the leftmost position. Okay, so you begin at the left of the unsorted position, unsorted portion, which initially is the entire thing is unsorted. So you begin with the leftmost card. You look all the way to the cards, all the way to the right end of the array, and you remember the smallest card. This is how this particular algorithm is different from bubble sort. Bubble sort just finds things that are out of order and tries to place them by bubbling them, if you will. Selection sort makes one sweep and remembers which card is the lowest card if we're doing an ascending sort, and then it swaps it with the leftmost card, which is the first card in the unsorted position. Okay, so we repeat all of this until the sorting is complete. And again, the difference here is that we're not making those extra moves that bubble sort makes. So here is our pseudocode. Again, it takes an array and the size of the array. The outer loop goes from 0 to n minus 1. So to less than n minus 1. Again, it goes up to, but not including that last one, because once we're down to the last one, we're guaranteed that it's in the right position. The J loop goes forward in this case. So this is one difference from bubble sort, which moves backward. The J loop moves forward in this case, and it begins by remembering that the least card it's seen is the card at I, and it tries to find a card that's less than the card at I, which is least, and if that's the case, then it remembers that card as the least card, and then finally it swaps it into position. Okay, so again, a picture is worth 1,000 words. Here is the algorithm. So we begin once again by saying I is the position that we're trying to nail down. Okay, so initially we're trying to nail down this position. Okay, and we sweep from here all the way to the end, and we remember the smallest value that we saw, and we swap it if it's less than this value. Okay, so we sweep the two smallest so far, the 3, the 8, the 1 is smallest, and we're at the end of the array, so we swap the 1 and the 5. Okay, and now we're trying to position this guy, and we remember 2 as least, and we sweep right. Well, 2 is less than 3, it's less than 8, it's less than 5. So we basically swap 2 with itself. That's what this is showing here, because it was already in position. Okay, we then have our index I become 2, which means we're trying to position here. Well, it's the same thing here. We sweep to the right. We find nothing that's less than 3. We basically swap 3 with itself, and the algorithm is actually does do that. And then we're in this condition, and I is index 3. So here's index 0, index 1, index 2, index 3. So I is here. We remember that value as least. We sweep to the right, seeing if we find something less than that value, and we do. The 5 is less than the 8. So we make the swap, and at that point, we're down to this last item, and the algorithm terminates because we know that we have reached, we're down to one item. We know that everything to the left is sorted, and so this one item is sorted because it's already been looked at multiple times. Okay, so that's selection sort. So why is it n squared? It turns out that selection sort is n squared in all cases. And so that's the case in the average case and the best case, etc. And as you can see, it does that much work, including swapping data with itself. Okay, so it does iterate through n minus 1 items, which is order n. Okay, and then for each one of these, like when I was trying to position the thing at the 0th element, I actually had to travel through the whole remaining part of the array. Well, that's the summation, if you'll recall, and that summation is n squared, because initially I have to look through 4 places, and then in this case I have to look through 3 places. In this case I have to look through 2 places, and in this case I have to look through 1 more place, right? So this is the summation that works out to be n squared. So this is an n squared algorithm in the number of data comparisons that it makes, and obviously it only makes the data moves that it needs to. It's slightly more efficient in the number of data moves than is bubble sort. But since the number of data moves is so tied to the actual layout of the initial data, we don't overly focus on that. There is no benefit here if the array is pre-sorted. If it's already sorted, we still have to say, I'm trying to lock in this, and I still have to go through all of these to confirm. Okay, so it doesn't make that many moves. It wouldn't make any moves in that case, but it would still do n squared comparisons. So that is selection sort.